so we're going to do this very, very quick, so I'm not going to have a chance to do all of the problems. I've only got about 20 minutes to try and get this done and post it. So we're going to go ahead and cover some of just the harder problems, maybe some of the problems that are a little bit more likely to be seen. I'll try to hit one of each problem. So I'll do one or two problems with trig. I'll do the ramp problem at the end. And that's pretty much about it. Those are going to be the harder problems. So on the review, let's go ahead and take a look at problem number 3. So if we start drawing our force diagram, it says we have a 10 kilogram box, and that is pulled to the right, or I'm sorry, it's pulled across the surface. We know there's friction because it tells us that the coefficient of friction is 0.2. So we know if we draw our force diagram, there has to be a force of friction here. It's on a surface, so there's going to be a normal force. There's gravity, so well, because it's an object, and then it tells us it's pulled by 100 Newton force. That is pulled at a 30-degree angle. So if we draw a line here, this is 30 degrees. All right. And it says, how would you go about finding the acceleration? Well, I'm going to show you how you'd go about finding the acceleration simply by finding the acceleration. So I'm going to redraw my force diagram here, just make it a little bit bigger. So we have the normal force, we have the force of gravity, friction, and we have our 30-degree angle here with our 100 Newton force. All right, now, something to be very, very careful of. While most of this stuff is going to be the same, for example, gravity is going to be negative 100 because our mass is 10 times negative 10. Like I said, we know that the mass is 10 kilograms, and we know that the coefficient of friction is 0.2. Okay, equations we're going to use. If you are given the coefficient of friction, that's your sign, or if it asks for it, that's your sign that you're going to have to use this equation right here. That's supposed to be an n. And then also we're going to have to use this equation over here, F equals ma. All right, now the thing to be careful is normally when the force of gravity is negative 100, the normal force would be 100. That's not the case, and here's why. We've got this other force right here that's pulling up. We don't just have the normal force and the force of gravity acting in the same direction. We've got another force acting in the y direction. So you got to be careful with that. So again, let's stop and let's walk through the steps. Step 1, are we at equilibrium? Well, we're looking for acceleration, so no. Step 2, draw a force diagram. We just did that. Step 3, do we have a force that's acting in more than one direction? Yes, we do. So we're going to go ahead and find our components. This force is pulling up and to the right. So I'm going to draw my components here. Okay, to find them, here's our y component because it's up. Here's our x component because it's to the right. Let's find y first. The y component of our applied force is opposite our angle, which means we are going to use sine. So it's 100 sine 30 degrees, which we will all remember is 50 newtons. And for our x component, that is adjacent. So it's 100 cosine 30 degrees. Now, I don't remember off the top of my head what that is, so let's go ahead and pull our calculator up here. Switch this. So, sine of 30 degrees. Oh, wait, no, I'm sorry. Cosine of 30 degrees. And then we're going to do that times 100. Gives us 86.6. All right, so here's what we're going to do. First, I'm gonna do something you can't do. You can redraw your diagram. You can choose not to. I'm just going to go ahead and move those components out into the directions they're actually moving, and I'm just going to get rid of this thing. We don't care anymore. We had that. We don't care anymore because we broke it up into components, and all of that, in the end, is all that really matters. So I'm just going to get rid of all this crap here. We don't need it. All right. with is this component here. The x component is 86.6, and this force up here is 50. Okay. Now, step 4, draw or write out the equations for each direction. So in the x direction, we have the force of friction and the x component. And because we are accelerating in the x direction, or we think we might be, that's going to equal F net. In the y direction, we have the force of gravity, we have the normal force, plus we have the y component of our applied force. Now, this box is not accelerating up into the air, so even though we're at non-equilibrium overall, our net force in the y direction is still going to be 0. Well, let's start plugging in what we know. We know the applied force up here, but we don't know friction, so that's not going to help us. However, we do know gravity is negative 100, and again, that's the mass times negative 10. We don't know the normal force, but we know the applied force is 50, the x component of the applied force. So what that means is negative 100 plus 50 is going to give us 50. I'm sorry, negative 50. So negative 100 plus 50 is going to give us negative 50, plus the normal force equals 0. Therefore, the normal force must equal 50 newtons. So, gravity pulls down with a force of 100. We pull up with a force of 50. The normal force takes care of the remaining 50. Now, to find the force of friction, I told you we were given mu, so we were going to have to use our friction equation, right? Well, now, since we know mu, let's pick a color. Why not red? Since we know mu, we can go ahead and use it. We know mu is 0.2. And again, this whole equation right here is just using this whole equation up here in the corner. So mu is 0.2. We know the normal force is 50, which means, I think that works out to be 10, but I want to make sure. 0.2 times 50. Yeah, okay, so that's 10. Now remember, this is not going to give you the direction. So because friction is to the left, friction is negative, negative 10 newtons. So now I'm using this equation right here. We have the force of friction is negative 10. We have the x component, which is right here, that's 86.6, equals our net force. Therefore, our net force equals 76.6 newtons. Last step, we have not used F equals ma yet, which means what we're going to do is take our net force, which equals 76.6 newtons, and plug that into F equals ma. Our mass is 10. And there we go. Now, I realize having this over 3 screens is kind of annoying, but hey, that's the advantage of YouTube. If you need to see anything from the previous slide, simply back it up, ignore what I'm saying, take a look at whatever you need to, and pop on back over here if you get lost anywhere on there. If you have questions, well, you know the number. All right, so that was number 3. I also want to go ahead and take a look at, let's see here. I told you ignore 1 and 2, those are the kinematics. 4 through 7, or the 4 force diagrams we can ignore. Number 8 is pretty much the exact same thing we just did, except it's different because there's no friction. So basically number 8 on that first page is the exact same thing, except there's no force over here. So you can cut that force out, and once you cut it out, well, all you're left with is this force here. That's your net force. You don't have to mess with this whole equation here. You don't have to find the normal force. You don't have to do any of this over here, so you can just cut all that out. That's number 8 on that front page. Let's see here. Tell you what, let's do number 4 real quick. This one should be a quick one. Again, this is a mostly trace. So if we have a wall with a ceiling, we have some object of weight W. It's got a string like this, and then over here, and we know that this force here is 30 degrees. All right. So what I'm going to do is draw my force diagram a little bit bigger. So we've got, that's just not right at all, actually. Hold on. All right, so what we've got here is we've got T1 here to the left. We have T2 up here at an angle. And we have gravity straight down. Now, again, are we at equilibrium? Yes, because this object is motionless. Step 2, draw a force diagram. We did that. Step 3, if we have a force in more than one direction, we break it up into components. In this case, we do. We have up and to the right, and we know this is a 30-degree angle. Now, here's the thing. Normally, we would break it up at this point. We would do the math. We can't do the math because we don't have an angle. We don't have a
Mr. McNamara, please go to the chili cook-off.
Yes, there's a chili cook-off. Don't worry, I'm not participating. My chili would make people sad. All right, anyway. So we have an angle. We don't have the side. So we can't do the math right now. What we're going to have to do instead is, if you read, it says the cable at the left exerts a negative 30 Newton force. Well, hey, we're at equilibrium. There's a force to the left that is a force of negative 30 newtons. That means somewhere there must be a force to the right of 30 newtons. And we only have one force acting to the right. That's this one right there. That x component, that top of that triangle, must be 30 newtons. In that case, that's opposite our 30-degree angle. So sine theta, in this case 30, equals 30 over T2. We multiply the T2 over, we divide over the sine 30, and what you get is T2 equals 30 over sine theta, which equals 60 newtons. All right, that's part A. Part B says, what is the force of gravity? What is the weight on this object? Well, we're doing pretty much the same thing with part B, so I'm not gonna keep going with it. But basically, if you want to find this force of gravity here, we are at equilibrium, which means this force here and this force, this component there, must be the same, because they're the only two arrows pointing up and down. If they're the only two forces and we're at equilibrium, they must add up to 0. You have a side, you have a hypotenuse.
Attention faculty and staff. The music has started and the chili is hot. Come on down to the South Cafeteria. Everyone is welcome.
I really don't want chili. I'm here, slaving for you guys instead of chili. You're welcome. All right, so force of gravity component, you've got a side, you've got a hypotenuse, you've got an angle. Use tangent, use Pythagorean theorem, you can use sine, you can use cosine. Use whatever you want. Find that angle, or find this side right here, and that's going to equal your force of gravity. That's your answer for part B. All right, I've got time for one more before I have to run off for my own exciting little things. Don't worry, it's not chilly. It's much less exciting for that, and that's saying something. All right, so running really quick through the rest of these. Problem 5, problem 6, problem 7, and problem 8. Those are all straight off your homework from, I think, Thursday night or Friday. Go look at them. If you don't have them, well, this is probably why you want to keep your old homework assignment. I have time for one more. So, we're going to do the rant. Problem 9. Okay, let's draw a ramp that looks slightly less creepy. Or more ramp-like and less, I don't know. Alright, so 20 degrees here, and we have a 10 kilogram block up here. So, normal forces, we've got the force of gravity down. If we have force of friction up here. 2 reasons we know there's friction. A, it does not say frictionless. B, it gives us the coefficient of friction of 0.15. If it gives you the coefficient of friction, like I said, that's telling you, hey, guess what? You're going to use this equation here. You don't have a choice. If you see the word coefficient, if you see the symbol coefficient of friction, you're going to have to use that. And then we have normal force, which for ramps are perpendicular to the surface. So, step one, are we at equilibrium? No, it says it's allowed to slide down the ramp, and it asks us for acceleration. Step two, draw the force diagram. We did that. Step three, do we have a force in more than one direction? But remember, for ramps, we have a quick little step we have to do in between there. We have to tilt this. We have to say, all right, our forces now, our coordinate system is x is up and down the ramp, y is perpendicular to the ramp. So, now we go ahead and we break our forces up into more than one direction. Our only force that meets that criteria is gravity, which has a y, it has an x. This angle here must be 20. The mass of our object is 10. Therefore, our force equals 100 newtons. That's our hypotenuse. So, part A, what is the value of the frictional force opposing the block slide down the ramp? Well, if we're looking for friction, let's go ahead and write our equation that includes friction. So, force of friction is in the x direction, and it includes friction and the x component of gravity, which is going to equal F net. Except, do we know F net? I mean, we can find FGX, but we have to find friction first because we don't know F net. We can't use this. Luckily, we can do something else. Luckily for us, we know the frictional equation. We know the force of friction. Or we're looking for that, I'm sorry. We know the coefficient of friction. What we don't know is the normal force. However, this block is not leaping up off the ramp, right? So if it's not leaping up off the ramp, what we know is the normal force must be equal to the y component of gravity, which we can find. The y component of gravity is going to equal the force of gravity, this hypotenuse right there, times cosine 20 degrees. Now again, I don't know what that is off the top of my head, but we can figure that out pretty easy. 20 cosine times 100. 93.97. So, we'll make that negative. Alright, so we'll make that negative. So what that tells us is if this is our y component, because we're not leaping up off the ramp here, our y component of gravity must be equal to the normal force. So what that means is the frictional force, I already started it, so we'll just finish it up over here. The normal force is going to be 93.97. Sorry, it's messy, but you get the idea. So once again, we'll just say 0.15 times 93.97, and that gives us a frictional force of 14.1, which hopefully is what I told you guys the answer was. Yes, 14.1 newtons. So the frictional force is negative 14.1 simply because it's to the left. Now for part B, what's the acceleration of the block? Well, we already wrote this equation up here. So let's go ahead and use it. We know the force of friction is negative 14.1. We know the x component of gravity, if it'll let me cross that plus sign. Okay, fine, it won't. Deal with it. We know the x component of gravity is...
Dave Cruz, please come to the attendance office. Mr. Cruz, please come to the attendance office.
All right. So we can find the x component of gravity by doing trig again, by saying FGX equals 100 sine 20, which again, going back to the calculator real quick, sine of 20 times 100 is 34.2. Okay, so we know this is 34.2 equals, so what this is telling us is our net force equals negative 14.1 plus 34.2, which, again, just for the sake of making sure we get the right answer, 20 20.1 newtons. And then finally, to finish up, if our net force equals 20.01 or 20.1, we plug that into F equals ma. 20.1 equals a 10 kilogram block times some acceleration. Acceleration equals 2.01 meters per second squared. Any other questions, text me. Good luck tomorrow.